Yeah, so in Tuesday lecture, we talked about the regularization and the regression. So today we are going to discuss and try some regression methods, okay? Let me see. Regression, so number one, we will do regression. And we will try some built-in function. Right, still, I mean, in the MATLAB. And then we will try the linear algebra solution, the normal equation. Then we will see how can we use explicit code for optimization to solve the problem of regression. So regression by optimization function, okay? Optimization, okay. Of course, this built-in function, when you use built-in function to feed your regression model, internally, that function was implemented using gradient descent. There's also optimization. But here, I want to show you use the generalized optimization function. You define your own model and you define your own loss function. How can you put that into this generalized framework? Okay, then we will talk about the lasso. Let's see, how can you use function in MATLAB to do this lasso-based regularization and to make your beta variable sparse, put a lot of beta variable values into 0. Then I will show you the lasso application in finding marker genes. Okay, if you have 2 clusters, you want to find, okay, which gene highly expressed in cluster 1, not expressed in cluster 2. So essentially, we will define just 2 values for cells with in cluster 1, you have a value as a 1, and then the rest of cells cluster 2 as a 0. So you actually will do a regression across all the genes, and then to use these combinations to predict your Y response as a 0 or 1. So you want to find those genes combination that gave you the best prediction as a cluster specific markers as 1. So that's, we will show how to do this using to find marker genes. Then at the end, we will play with a real data set. So this is from a human protein concentration sampled from a lot of lung disease patients and with healthy control. So we will get the Excel sheet table and see how can they do classification. Okay, you build a classifier so you can use those concentrations of proteins to distinguish patients from the healthy control. And then we will see how can you use lasso to identify those genes which most responsible for the separation of different cohort. And within patient group, we also have moderate symptoms, more severe. So it's a index variables you can assign to each individual sample. Okay, so that's the outline for today. And here we, what you will prepare will be download the real data set. Okay. I already put into this Google Drive folder. We have two Google Drive folders. You can use either of them. And within here, you see this called human_proteins. So these files are what we need. We really need is this Excel file. So if you can download this to your local drive, and found it, and also if you have this Excel file, it should be in the download folder. You may want to copy or move it to under your MATLAB working folder. Okay, what I did is copy and paste to here. So that's your data. We will work on later. Okay. Okay, now I'm on my PowerPoint slide I used in Tuesday, and let's switch to page. This is page 29, slide number 29. I want to use some of this source code so we can have the data to do our regression test. So what I can do is to copy this. Okay, if you don't have the PowerPoint at this moment, I will paste this code into chat. It is copy and paste. Should have X and Y. X is some of these two variables, weight and acceleration, and Y is your MPG, okay, mileage per gallon, basically. And we have (94) samples, okay. So that's our independent variable, which we are going to use independent variable in X to explain Y. Let me know when you are ready so we can move forward. Ready? Okay, good. Okay, so if you look at X, is 2 columns. First column is the weight, and another is acceleration. We can have a quick scatter plot to look at the relationship between X and Y. So I will do scatter plot X, then I use first variable and regress against the Y. So all right, so it looks like there are negative correlation. So I expect a slope between X1 and Y should be negative. Then try the second variable. Okay, so this is not so clear, and the acceleration seems not have a very strong correlation with the MPG. And you can also try 3-dimension, scatter 3, and let me know if you can do that. If someone can do that, then paste your code into chat. 3-dimension of this 2 input variables and 1 output variable. Can you generate a 3D scatter plot? That's the way you can have a quick illustration of your data points and see roughly visually detect some relationship between variables. Anyone knows how to do 3D scatter plot? No? Yeah. Mm-hmm. Yeah. 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 I think I just get it. I'm surprised there's nobody online can paste the code. Okay. So that's the way to do it. Okay? So let's give you 3D scatter. To rotate, you do you stay like this and do the rotation. Okay. You can also label the X. Then you single quote to give the string. So this is weight. Okay. And Y, it's acceleration. Z is the value. Okay, so once you have this annotation, you can look at the relationship between variables. So if you rotate to this angle, you should be able to look at the relationship between weight and acceleration, because you look at from this angle. Okay, as we expected, you expect some negative correlation between these two variables among these 94 different cars. Okay, so let's be clear what we are trying to do. We're trying to do the regression. We want to use acceleration and weight and the two variables to explain MPG. So once we have this model built and trained with the data currently we have, then we will be able to predict if you have a car at certain weight and acceleration, then you can predict its MPG, okay, because you have this theoretical hyperplane to use two variables to explain the third. You can also detect, for example, which existing points deviate from the expectation most. For example, this one, if you build a model, you will realize the error you will get between observed and expected for this particular car may be greater than the rest of the points, because most of the rest of the points seems on the global trend of this correlation, but there's some different cars just jump out. So that's the way you can use regression model to detect the unexpected deviation, and you can see, okay, this is outliers, okay, more like outliers than the rest of the car. So you have these 3 points maybe. Okay. Your model in general just not able to predict very accurately for them. Okay, so let's use the built-in function to do this. Let's see, in this case, this part is optional, okay? The reason I put that in -1 indicate I don't want to do the slope, not the slope, the intercept. In general, if you don't put anything, you will have, by default, it's something like this. You use 2 variables to explain why. So if you don't put anything here, there's a model you define. If you do this, you will have intercept x1, x2. Okay, by default, your model is this. There's 1 will be automatically put in to help you to do this intercept with 1 more variable automatically. The reason I put this particular way to to stop let the model to give me intercept, because I want to show you the result is the same as the rest of this the other method. Okay. In other ways, so I didn't normalize or standardize x1, x2. If you standardize, make them into 0, around 0 as a mean, and then you don't have to estimate this intercept. Okay, but in this case, we need intercept because we have the full model need that to explain basically the scale the variables. Okay, so if you use this non-intercept model, and we will get the prediction of coefficient, which this two. Okay, you can try both +1 or -1. When you have a +1, you should have intercept. If you have -1, this intercept will be ignored. We use this intercept ignored model because we want to make this consistent with other computation, even though we don't normalize our data.
So is the +1 -1, is that actually setting the intercept, or is that just a flag for MATLAB?
If you don't put anything, MATLAB will automatically give you this +1.
Right. So you're not setting an actual constant for the intercept, but it's just a flag, I guess, then?
Yeah. So if you don't put anything, you see here, so by default, it will automatically add that in. So that's a built-in function. It's called fit linear model will do.
Okay.
Will do it for you automatically. So if I click written here, you see the model, it automatically generate is to use x1, x2 plus intercept to explain why. The reason you have two variables here because the function detects there are two columns in there.
+1 is predicting the intercept,
Mm-hmm.
and if you're doing -1,
it's just ignore, tell the model, ignore intercept.
So it doesn't add that like face value?
Mm-hmm. It will regress cross origin, the line, instead of doing intercept, it will just,
0, 0,
yeah, yeah,
instead of whatever the calculated.
That's right, yeah, you force the model to have a regression line cross the origin 0, 0.
Okay.
Mm-hmm. In real application, you certainly want to have intercept, but for this demonstration, I just expressed that parameter in order to numerically to show you get the same result with other normal function. Okay, if you do this by default, you will have intercept, you have this, you have that. And as we already seen, the correlation between your variable 1 and the y should be negative. You see the negative. So that's fit our impression. So I will just go back this model. Okay, still, and negative correlation and that's positive for the second. Okay, so that's what you should do to use this built-in model. Predict those variables. And next, so we just use the matrix inversion of matrix to do it. So if you have a value, say a equals 3, and then you have 1/3 over a is a B, and then you have a B times A, that should be 1. So this is just a apply for the single value here, but if A is a matrix, for example, now you have a matrix of a random 3 by 3. So you want to find a matrix B, and so the B times A becomes identity matrix. So the B will be the inversion of A. So that's a definition. You just cannot do this A1 over A. That's different. That's different. It's not a matrix operation. So you need to have a you probably can do this. I'm not so sure. Yeah. So that's your B. Then B times A becomes identity matrix. That's the definition of inversion of matrix instead of a single value. So this function I gave you identity matrix defined. So identity matrix means you have 1 in the diagonal and 0 of the rest. So this function is this, gave you this, okay? So in our model of this is we have X, we want to B, and so we want to X times this variable to be Y. So that's our regression model. So in order to get the values of a B, so you can use X divided by Y, right? Divided by Y. So that's the B. So what we expect to do this. However, you cannot do that because this operation is not valid. So it's not direct divided by Y. I hope it can work. Not degree. So this just not working. Okay? It just cannot. Okay.
You can do dot slash.
Dot slash. Okay. So that means slightly different things. Is this element based? Okay. So you divide the first column by Y and each by H. So that's element based. It's different from what we are trying to do here to estimate the B. So B should be 2 numbers, okay? And results should be B1, B2. But if you do dot operation, so this will be item based. The first item of X1 divided by first item of Y1, second. So that gave you the 94 element vector in B. So that's not what we expect to see. So what you can do is do the inversion. So I'm doing to invert this, okay, times B times Y. So the inversion function has a limitation. X has to be squared matrix in order to do the inversion. So the pseudo-inversion function can take that. So you get this, and let's see what the model generated. The model, we have a parameter. Coefficient. Yeah, let me find the model, the answer. So the model answer is the beta 1 is negative 0.001, and beta 2 is 1.89. Yeah, it's the same as this, right? Can you see this, the same? Use a built-in model, you get this value here, and this simple function also gave you the same answer. I'll do that again. So our model, we build in the model without the intercept to get x1, x2 beta value of this, and you can just directly get by inverse and times x because okay, the same. So that's what I want to show you is you can just use linear algebra to invert your X matrix and times Y, you get B because your model is Y is X times B. Okay, you just invert that, you get that. Of course, internally, this is not computed by this inversion function. Computed using optimization. And then we can try more general yeah. So we had a problem. So remember we had errors if you apply the inversion function to this, because X is not square matrix, you cannot do it. But the normal function to do this transposition and will allow you to do it. Okay, so that's our yeah, so that's our normal equation. Here, remember this. So you have X transpose times X is become a dot matrix, not dot, yeah, dot product between the matrix. So you have a 2 by 2 matrix here, and then take a inversion of that matrix times X transpose times Y. So we have this function, and if I just reply this, I get the same answer here. So this is a direct copy of the definition of normal function to show you, okay, that's true, and you can just compute beta variable values by using this. This operation -1 is the same as doing the inversion, so let's apply to a squared matrix. You get the same answer with this. In fact, if you try all the expression I provided here, you get the coefficients. So every single one of these to get the same answer. Especially you have this backslash x \1, and that's a very special operator, and who gave you this linear regression solution. Okay, so the last piece is to use SVD to decompose it, and then to use the decomposed results to do this inversion, because X was squared matrix, but if you decompose them and then you can inverse this S matrix, but it's a diagonal matrix. And then this is shortcut to do P pseudo-inversion. So in pseudo-inversion, if you look at the function of source code, it's doing this SVD. We will talk about the SVD next time. So if I do this INV, then you will show the source code of this, how the pseudo-inversion was computed. So that's the source code provided by MATLAB itself. So you see here, use SVD function to get that, then compute the inversion in this way. Okay, I think that's all for normal equation and using this linear algebra operation to achieve linear regression estimation for the beta variable, beta values. Any questions? I hope this can help you to understand this normal equation and what the linear. So you have all this this way and a new way to express your linear regression model using matrix operation. Okay, let's see how we can redefine this as a normalization problem. So let's see, I will create a new script. See, I will see this like script number 1 underscore optimization read. So I can create a working file, so I can type in some source code and also save the script for later use. Okay, by the way, I have never done this myself. I'm just doing this online here and see whether we can get that. Still, we are going to use the same input as an example. So I'm going to still copy this. So I have X and Y to be preload. Okay. So I can have this 2 percentage signs, so gave me a blocker definition in this source code editor, and then see, okay, the load data X and Y. Okay, so that's the purpose of this. So I can run this section. I click this, and this active section will be executed. Now, I need to define a B. So I will start at B. So B is our target. We want to have 2 values here. I gave this 2 zeros as the initial value. Okay, maybe call it B0. You can have anything in the, okay, 2 initial estimation of 2 slopes. So this initial value for your lost function search. Okay. The function in search, I'm going to use this, and then we need to define a likelihood function. It's a loss function. Okay, I just leave it there and not do anything. The second will be my B0 initial value. And then I need to give X and Y. That's my data. So I hope this will give me the solution. The solution will be the okay. That's the framework to try to use the likelihood function. Because let's solve the loss function. Okay, I have data, I have this. My definition of my B is, so now I'm going to define this loss function. So I gave, so I'm going to define a function called function here. Okay, this loss function will take it a B and also X and Y. Hope I can make this correct. And the cost. Okay, output is C. So what is the cost? Cost is X times B. X times B is for any given variable, beta 1, beta 2, I multiply it to give me the prediction. So that's my prediction, and Y is my observation. So the difference between them and the norm. By the way, there's a norm too. This is the cost. Okay. So that's why I want to make this smaller as possible. I have an observed Y. I have my given B, and I use B to times X to predict my predicted Y and the difference between them. That's my loss function. Yeah, but that's a basic structure. I'm not so sure in some details whether my code will run right now. There are some syntax errors I expect to pump up. So for example, how can I pass on these two variables into the loss function? Maybe not right here, but I just give it a try and see what we can have. I just run this section. Okay, errors in here, error must be optional. So the third variable, I just give empty. Okay, because the function f minimum search want to have some optional structure. I just provide empty variable to give, let it to use the default. Okay, maybe we should put a, so here indicates, I can see, okay, there mismatch between X and the B dimension. So instead of put a row matrix, row vector, I will make initial value as a column. So I can maybe can work this out. So be instead of a row vector, I make it into a column vector. Okay, what's the P? Yeah, so I got the answer. The B is this. Looks like very similar to the solution we have, right? Okay, so this is a demonstration to use general search engine, just fit this image. Which B parameters to give me the best solution, which Y and X times Y is the most similar to each other. You can initialize this with anything, and the 2 zeros, which should also work because it's robust against the initial guess of this. Okay. Just play with this, and I'm surprised I can make it correct in a couple of trials, and it works. Okay, I will give you 5 minutes to think about this and make sure you understand what's going on here. Why the loss function is defined in that way. What's your objective to search? Okay, objective function. What's your objective here? And how I used that function and how the parameters pass on it. And then we will take 5 minutes break, come back at 11 o'clock. Then we discuss lasso. Okay.
I think your microphone might have cut out as well, actually. Where is it? E.
Mhm.
This is essentially calculating the lambda for that and including everything.
No, this will calculate, try a lot of lambda, so you have a solution, say, pick 100 genes, top 100, top 50, so there are a lot of, and then you select one of the column, give me the 10 non-zero values. Okay, in the last 30 minutes, we will download a new data set. And this data set is a protein concentration measured in over 100 human samples. Some of them are diseased patients, some of them are healthy control. And with this huge data set, we are going to do the classification and also lasso analysis to see which protein concentration can be used as a predictor to predict the outcomes of this disease status. So I'm going to clean my desktop here. If you haven't downloaded the Excel data from the Google Drive, you still have time to do it. Once you download it and copy that file and put into this working folder. So I'm going to right click and open outside MATLAB so I can bring up Excel to see, to take a quick look of this. Okay. Let's first look at this original. So that's what the data I received from collaborators. We need to take a look and do some cleaning and also pre-process this so we can load the meaningful data points into the MATLAB to do the classification. If you check this and they have the protein accession number here and then corresponding genes. So it's not a one-to-one, and the some accession number correspond to more than one, some genes corresponding to more than one accession number. And the organism is a human, so this complete column is useless. It's all the same across this 9,650 protein markers. Okay. Some of these accession number has no corresponding protein name, gene name. And then those columns are not very useful, and we can delete, we can remove them later. The meaningful columns start from the I, and those are the samples, and this individual ID. You cross this, you see first there are missing values. Okay, that's all realistic. We always have missing values. If you have, especially this kind of clinical data. And then after this yellow highlighted samples, they start to have this light gray colored, and then slightly darker shaded. And then they have annotation here. Yellow is control, and mild and moderate and severe condition of the patient. Okay, so this original spreadsheet you just cannot use because you have all this annotation there. So you have to do some cleaning, and then I make a copy and clean all this, get rid of some of this incomplete. So in the input is the one I already cleaned up. I get rid of some columns, keep useful information, and delete the useless sample, incomplete sample, and also those annotation that will be will not be able to import correctly. So now this table is complete and in a good shape for the input. Yeah, also extract this first two columns here and to make it easy for later. Anyway, so I make a new input spreadsheet, and this one then I also transpose those ID, the names, and label it with 0, 1, 2, 3, right? So I make this label. Then spreadsheet 1 is transposed. Remember, here is gene by sample, and here I transpose, make the sample by gene. Okay, and also the sample because we don't care about individual samples, we just care about the category. So those are the controls, and anything greater than 0 will be patient group, and patient group was defined by the severeness of this symptoms into subclusters. Okay, so in this spreadsheet, the sheet number 1 is the completed data that I will import, and this will be responsive the variable to categorize samples, and the rest of them are the features. And you can search from each of these by looking at the table of gene to see, okay, which accession counterpart is which from which gene. Okay, is that clear, everyone? We are going to import this matrix into MATLAB. Clear? So if we don't have time to finish everything today, I will leave this as your homework. Is that fair? good practice actually. You have this real data set. Okay, so now let's make this a homework, okay? Now, everything is recorded here from those, so you can come back and review, and because we have the data already, I just show you how to import that and make the matrix, make the response variables. Then your job is to do a classifier, and so we can predict the outcomes, and you want to find a way to select which protein will be useful, give you information to separate those samples. It's a small machine learning project. So we will read table. Read table will take a file name, so that will be there are multiple spreadsheet in there, so this should be option sheet number 1. Okay. There's some warning message, but it's okay because the name of the sample, the accession number may be changed. So we will make a yeah, so this will be the Y. Okay. Okay, now you have your X and the Y, which extract from imported table by some of the conversion, and then okay, so to give it a try and see how far you can go. So I will read another spreadsheet in. This is a gene. So I have this small table. I can, the X, we have 9,650 genes, and this table will tell you the name of each gene. Okay, so that's a table for gene, small t. So that's a starting point for your homework. There's no hard solutions in which kind of goal you need to achieve in order to complete this homework. You just try and see how far you can go. That's the soft solution, soft goal. And there's no yes or no answer, because for this data, we don't have the real answer. We don't know. It's exploratory, and we don't know which proteins, which combinations will give you the meaningful solution, whether those patients can be separatable or not. There could be noise in their mislabeled or misclassification from a clinic. Noise in the data sample collected different time, and we don't have covariant information about the gender, sex, age, ethnic group of those patients. So we have no idea. I will post this information in the homework and the Google Class, and then so the classification and the lasso is what I can think we can do, but you may have some other ideas. Okay, you certainly can do t-SNE and to look at whether genes are grouped together by patients, or patients can be grouped together by their gene profile, protein profiles. What else you can think about? we should have a lot of open questions for this data set. There are missing values in this matrix, so I suggest you have to find a way to do the imputation sometime. Or you want to clean some of the samples of protein. If the missing value is too missing values, there's too many of missing values involved. Okay, that's all, and for this week. Please let me know if you have any question now or during the week. Otherwise, I will see you next Tuesday. Have a good weekend, everyone.